Hello, everyone. My name is Rudy Leibrandt. I'm a product manager at Snowflake, and I'm responsible for the Snowflake query platform. Today, we're going to take you through how we make the fastest engine even faster. And with me is Noah Arliss.
Hey everyone, I'm Noah Arliss, the Director of Engineering here at Snowflake, and I own the Core Query Platform teams. And we're excited to share with you some of the work that these teams deliver on a regular basis.
So, what you can see here on the left of my screen is a scrolling window of the performance optimization we've rolled out over the last 2 years. On the right hand side, you can see a more recent list. Each of these improvements make queries on Snowflake run even faster. Today, we're going to talk about how we make the fastest query engine even faster, and some principles that we wanted to discuss is that we deliver these performance improvements every week without requiring any code changes or configuration changes on your side. The outcome is that you see improvements in price for performance, so you can do more with Snowflake over time. These are also compounding improvements, they're layered on top of each other. Let's take a look at the impact of these improvements over the last 12 months. To understand the impact of these improvements on customer workloads, we developed a scientific method to help measure Snowflake performance over time, the Snowflake Performance Index. We designed the index because reliably measuring performance across workloads with data shapes that are ever changing is hard. Synthetic benchmarks such as TPCH and TPCDS also do not represent real world customer workloads. You can compare the SPI or the Snowflake Performance Index to a stock index, such as the S&P 500. The SPI indexes query duration over hundreds of millions of queries every day. And as you can see here with the SPI, we are able to measure a 1.8 times improvement in query duration over the last 12 months. Noah, why don't you take us through how the engineering teams also use the SPI?
Sure, Rudy. As a part of building the SPI, we created the ability to break down queries into their distinct components and drill in for more details. One element we can dig into is a breakdown of statement type for queries within the SPI. In this example, you can see that select statements represent about 40% of the overall SPI. We can further drill down into these statement types to find hotspots to focus our attention on. There are also other ways to slice and dice the data, such as warehouse and cluster sizes. This is one of the levers through which we prioritize our work, but it's not enough to identify impactful improvements and develop them. We also have to roll them out to production without regressing the system. As we've discussed, applying the scientific method is an important part of our process here at Snowflake. For each and every feature, especially performance features that we ship to production from the core engine, we can leverage a tool that allows us to run end user queries in an obfuscated way on our own warehouses on our own dime. The tool can replay queries with features turned on and off and verify that the results between runs aren't different. This tool not only verifies that the results are not different, but also allows us to confirm that the feature has actually improved performance. For each optimization, we can identify which queries are most relevant to make sure that we have the best coverage possible. With an adaptive system, catching all possible regressions for all possible edge cases is really hard. We have extensive internal testing infrastructure, but it's impossible to cover every edge case for an adaptive system that runs billions of queries a day. This functionality allows us to ensure that our optimizations and adaptive techniques are working in the real world. It's one of the first steps we take after we validated a change internally before we begin rolling out an improvement to production. Before we go any further, it will help to understand Snowflake's architecture at a high level. Rudy, why don't you start us off?
As many of you know, Snowflake's distributed query engine has multiple layers. Let me try and take you through a simplified life of a query. So to start, you can imagine a query is received by Snowflake via one of the query interfaces, such as ODBC, JDBC, or even the Snowsite interfaces. Then we see if we already have the results for the requested query cached from a previous execution. And if we do, we'll return those results immediately. If we don't have results cached, the query will then go through the core optimizer and would build an execution plan. Then we'll prune data. The optimizer will use metadata to identify exact underlying data that needs to be processed by the execution engine. We then send the plan to the distributed, vectorized, and columnar core engine for execution. This is the virtual warehouse as you know it. The warehouse will only scan the necessary data from local or blob storage, process the data, and then return the results back to the client. Then, of course, as a part of returning the result, we will also cache the result for future use.
Thanks, Rudy. Under the covers, a table consists of micropartitions as well as metadata about them. A micropartition is an immutable file kept on cloud storage in a columnar and compressed format. Typically, these micropartitions are 16 megabytes in size. Metadata is stored separately from the data and is used to tell us which micropartitions belong to the table, along with stats that are used to help ensure we only scan relevant files when answering a query. As you can see in the diagram here, the micropartition is in columnar format. In the example above, based on the filters, we only have to scan a single micropartition to answer the query. Rudy, would you mind taking us a little deeper on micropartitions? And then I'll walk us through a simple real world example.
As you said, micropartitions are immutable data storage files, and they're structured using hybrid columnar storage. Columnar values are grouped together for better compression when storing them and better performance and bandwidth when scanning data. On the right of the slide here, you see an overview of this format. First, there's a header that explains where each column is located in the micropartition, along with the relevant metadata such as minimum and maximum values, numbers or nulls, or numbers of distinct values. Later in the session, we'll talk a little bit more about how pruning uses this metadata to avoid work.
Thanks, Rudy. I think it would help if we walk through the basics of evolving micropartitions in the system. Let's take a look at an example table with two columns. First, we'll copy into the table, then we'll insert a row, and finally, we'll remove a row. When we copy the data into the table, Snowflake will create two partitions, each containing 3 rows. We'll pull out some stats, including min and max values for UIDs and name, and we'll store that in metadata M1. When we insert into the table, Snowflake will add a third partition, which will contain a new row for Martin. It will also create another metadata element M2 with stats for the new partition, in this case, 7 to 7 and M to M. Finally, when we remove from the table, Snowflake will delete partition 2 from the table and create a new partition, partition 4, which will have the remaining rows Florian and Thierry. It will create an updated metadata element representing the new partition as well. As you can see, for each DML operation we create net new micropartitions because once written, they are immutable. In addition, as you'll see later on, the metadata will be leveraged in lots of interesting ways to make the system performant. Now that we have a basic understanding of micropartitions and metadata, Rudy, would you mind walking us through how we optimize them today?
Sure. So, the first thing is we have to strike a balance between partitions that are too small and too large. When partitions are too small, we will have a lot more files leading to metadata and storage overhead, which will affect read and write performance. On the other hand, if partitions are too large, we can run into pruning and clustering efficiency issues. Right sizing partitions is important to ensure that we get the right trade offs between writes, reads, pruning, and clustering. Internally, Snowflake optimizes micropartitions during query execution, where we estimate compression ratios and then merge the data from multiple workers or split partitions as needed. There are also background processes that will optimize micropartitions outside of query execution.
What about semi-structured data, Rudy?
Well, as we know, unlike structured content, JSON documents don't have a predefined schema. This makes it a challenge to take advantage of columnar data storage. To address that, we store semi-structured data in our variant data type, which provides automatic type inference and columnar storage for schemaless data. Here, we have an example where we insert two JSON records with different fields. Snowflake automatically detects that name and ID are common rows across that table. Those fields are then extracted and stored in columnar storage with the appropriate types. We call this process subcolumnarization. Fields that are not common across rows, or those that don't have the same types, are stored as the binary representation of the nested object. Then, extracting frequent common paths and storing them as columns allows us to take advantage of compressed storage, similar to regular structured data. Moreover, we can then use the same benefits that structured data gets from micropartitions in terms of efficient pruning and scanning by collecting and storing specific metadata about each individual column. Semi-structured data often evolves over time. New fields are added or existing fields are changed and removed. And then Snowflake performs subcolumnarization at the micropartition level, allowing us to adapt columnarized data as the schema evolves over time, where some fields become common and as others disappear. Next up, we'll discuss how we optimize queries. Noah?
If we take a closer look at the lifecycle of a query, the first major stop is with the compiler, where we parse the query into an internal representation, perform semantic analysis, query rewrites, micropartition pruning, and cost based optimizations. When done, we'll have a physical execution plan for the runtime to execute. Parsing extracts different clauses from the SQL text. Semantic analysis is used to understand what each object or column referenced in the query mean. Logical rewrites optimizes the query plan by reordering logical query operators. Partition pruning reduces the set of micropartitions that the runtime has to scan. Initial plan generation is where we create a plan and perform additional optimizations like constant folding that we'll discuss later as part of plan rewrites. Cost based join ordering leverages statistics about the data to find the optimal join order for the runtime. Finally, we generate a physical execution plan for the runtime to execute. The ultimate goal here is to do the job with the least amount of work, which is why metadata is such an important part of the system. Snowflake metadata leverages a hierarchy from table to micropartition to columns. This hierarchy is essential to support datasets ranging from megabytes to petabytes. We also compute stats for number of distinct values across micropartitions, and these values are always kept up to date as they're automatically computed during query execution, as you saw in the DML example earlier.
Yeah, that's right, Noah. Metadata is a key ingredient in allowing Snowflake to answer queries with a minimum amount of work. Snowflake avoids scanning entire tables by only scanning the columns that are accessed from the query. We also use column metadata to avoid scanning rows that are filtered out. How much data can be pruned depends on the filters and joins that appear in a query and the clustering of data in tables. In the example you can see here, in order to return results for this query, we only need to scan one micropartition, micropartition 4. We know that no other partitions contains the 11.4 value, and none of these rows match the filters in the query. Using this metadata is not just limited to pruning micropartitions, and in some cases, we can answer predicates without scanning any data at all. During the optimization phase, we can recognize that a filter predicate such as date is less than 11.2 can never be true based on the minimum values across all micropartitions. This means that we don't need to scan any rows to evaluate the predicate. It is always false. This is called constant folding. Constant folding can also happen for expressions in different parts of the query, by example, in the select clause with a constant value based on the metadata information. So now let's get into query execution. Noah, you can take it away again.
Snowflake's query engine was built from the ground up to leverage the columnar micropartition architecture we've been talking about. By being columnar, we can make effective use of CPU caches, SIMD instructions, and compression. The engine is also vectorized, which means that the core operators can handle batches of a few thousand rows at a time and avoid full materialization of values wherever possible. Finally, it has a push-based flow control where operators are pushing results to downstream consumers, allowing for data to be processed in a pipeline fashion. To explain in more detail, let's look at an example query. Here we have three operators in the query execution that scan the data from the micropartitions, then apply the filter on the age column, and finally compute the projected name and tax. Since the engine is columnar, the scan only reads relevant blocks of data from the micropartition and pushes column values in batches to the next operator. The vectorized filter operator evaluates the filter condition as a vector using SIMD operations. And finally, the projection operator performs a vector multiplication to compute the tax. One of the biggest challenges in cost-based optimized systems is inaccurate stats, which can lead to inefficient query execution. One of the coolest things about Snowflake is that it uses adaptive execution as a way to solve this problem. Instead of statically executing the query plan provided by the optimizer, the data flow engine can make local and distributed decisions. There are side channel communications between operators, and decisions can influence data distribution within the cluster as well as operator behavior. Rudy, would you mind walking us through one of the runtime optimizations in the system?
Yes. Let's take a look at adaptive execution in the context of aggregation and aggregation placement. Here we can look at an example where we have an aggregation after a join operation. Normally, the aggregation is applied to the result of a join operation, but in some cases, we can additionally aggregate values before performing the join. This could potentially reduce the number of rows that are sent to the join operator. And in that case, we'll end up with two aggregation operators called the child and parent aggregation. This technique, however, cannot be applied to every aggregation in every query. And Snowflake's query engine relies on adaptive execution to apply this technique only when it helps. So let's consider two cases. In the first case on the slide here, the child aggregation reduces its output rows to 10% of its original input rows. We can see here that the join explodes and it produces 10x more rows compared to its write input. Here, we measure cost as the total number of rows processed across operators. In the query on the left, with aggregation placement disabled, we process a total of 120K rows compared to 21,000 rows when enabled, and that's a 90% reduction in rows processed. When running the query, we detect that the child aggregation is considered beneficial and therefore keep it enabled during query duration. Here's our second example where child aggregation optimization does not make things more efficient. In the example here, the child aggregation reduces its output rows to 70% of the input rows. The join does not explode and produces the same number of output rows as the input. When enabled, the total number of rows processed, however, is 24,000 as opposed to 20,000. The child aggregation makes the downstream pipeline a little cheaper, but the total cost is higher compared to the cost when it is disabled. So Snowflake automatically detects this and dynamically disables the extra aggregation to avoid regressing performance.
Let's talk about another example of adaptive execution. Snowflake also makes adaptive decisions around distributed hash versus broadcast join. With broadcast join, results from the build side of a query are broadcast to all nodes to join against local values. Whereas with distributed hash join, values are first partitioned across the cluster using consistent hashing and then joined respectively. Choosing the right join strategy is very important but also challenging. For example, when the build side of the join is small, broadcast join is significantly more efficient than the distributed hash join as it avoids redistributing the larger probe side. On the other hand, when the build side is larger, it will not fit in the local memory, forcing workers to spill to SSD when they perform the broadcast join. Additionally, the cost of broadcasting the build side could become comparable with the cost of redistributing the probe side. That means that the distributed hash join will be the more efficient approach. Since knowing the input sizes and key distributions during optimization time is extremely difficult, we rely on adaptive execution to pick the right strategy. Snowflake will first hash the partition on the build side and collect global memory usage. Based on memory usage, the system will make a runtime decision on which join method to use. If the build side is large, like 64 gigabytes in case 1 here, it redistributes the probe side and continues the operation as a distributed hash join. However, if the build side is small, as in case number 2, it will use broadcast join.
Snowflake also has mechanisms to deal with data skew as well. Let's talk about join skew handling as an example. Normally, each partition is processed by a single worker. However, if there's a disproportionate number of popular keys on a single partition, query processing can be slowed down dramatically. The skewed partition will become the bottleneck in query execution. This is particularly problematic as using more resources, such as a large warehouse, does not help speeding up the query at all. All other nodes will remain idle as the data is being processed in the node with skew. To address that, the Snowflake query engine automatically detects the situation during query execution. When that happens, the popular keys are distributed to all nodes to eliminate the need of a single node joining against the popular keys.
Snowflake also leverages previously materialized results on multiple levels. With a warehouse, we have a data cache that will save us from needing to go to blob storage again. We also have materialized views, which save time by reusing past computation. And finally, result reuse, where we don't execute a query at all. This takes us through some of the key parts of the system that make Snowflake so efficient. Now let's review some of the most recent performance improvements we've made to the system. First up is partition granular selectivity estimates. This is a performance improvement we added in the optimizer. Rudy, could you tell us more about this enhancement?
Sure, no. Estimating selectivity of filters is critical in making join ordering decisions. With partition granular selectivity estimates, we use micropartition level metadata to estimate selectivity at the micropartition level and at the table level in aggregate. This gives us much more accurate selectivity estimates, which will improve those join decisions. This performance improvement applies to 1 million queries an hour, affecting more than 80% of all active customers in Snowflake. In some cases, query execution time was reduced from 2 hours to 10 seconds. Noah, would you mind telling us about top K pruning with limit and order by clauses next?
Absolutely. Top K queries retrieve the K highest or lowest ranked results based on search criteria, typically using the limit and order by clauses. For those queries, we speed things up by leveraging metadata to stop scanning when we know that none of the remaining rows can be part of the result. On average, top K queries with limit and order by have improved by 30%, with some cases improving by over 100x. What about improvements to hash join broadcast decision, Rudy?
Yeah, earlier you spoke a little bit about broadcast join decisions. Snowflake will make an adaptive decision to do a broadcast join based on memory usage. By looking more holistically at the memory for an entire join chain, instead of looking at each join individually, we can reduce the probability of memory errors during execution. This improvement has reduced the rate of memory errors in aggregate in production by more than 14%. We've also seen a reduction of single query memory errors by 50%, and for some specific customers, we've seen up to 10x improvements. That's a lot of query retries avoided and new queries that are successfully running. What about network encryption, Noah?
Right. For network encryption, we actually made a few changes. First, we moved to a more efficient encryption algorithm that maximizes throughput between warehouse nodes by improving parallelism. Second, we took a look at compression and when to use it versus not, making the decisions adaptive. These changes can improve query duration by up to 40% in some cases based on internal benchmarking and leveraging the SPI.
Before you leave us, we'd like to demonstrate one of the adaptive optimizations that we discussed earlier in the presentation. So what we can see here is an example of aggregation placement. So let's see this in action. In the recorded demo, you'll see the same query executed with and without the optimization enabled. And we'll look at the query profile for each of these. So you can see here is that this query contains a few group bys, a bunch of joins, some filters. And what we can see here is an aggregate. And what we'll do here is just execute that. And then I'll step on to the query profile next. So before we enable the optimization, what you'll be able to see here is that we start this query with 2 billion rows coming out of the table scan. Towards the top right, you can see that this query executes within 17 seconds. And what you could see is how the data or the rows from that table scan flows up the query plan, up the pipeline, and then towards the end of the execution, we execute the aggregate and reduce the rows to the final step. So as we discussed earlier, you can see that we pass data all the way up to the tree before reducing the rows. So let's look at the after query, and no surprises here. It's exactly the same query, the same group by statements that we had earlier, and the same filters. And what we'll do here is we'll just highlight this, and the aggregates at this line here, and we're going to see what happens when we enable the aggregation placement feature right now. So we'll execute this query, and then we'll take a look at this query profile now. So towards the top right there, you can see that we're still scanning the same amount of data, but now this query runs in 5 seconds. So that's a 3x improvement. When we look and we scroll up the query profile to see what the optimization does here is we can see we start with the same almost 3 billion rows from the table scan here. And now the aggregate is placed just underneath the join operator here. So we can see that we reduce the work by almost tenfold out of that aggregate. And as we go up, we can see that the parent and child attribute relationship, and we reduce data as we go up to this thing. So to summarize, what you've seen here is an example of adaptive execution using aggregation placement. And this change happened without you having to change a single line of code or any configuration in your Snowflake environment. Thank you for spending time with us. To keep up to date with performance-related features, you can follow the Snowflake performance release notes in the documentation. You can read more about these kinds of performance optimizations in our engineering blog, and we'd love your comment and feedback on those. Finally, follow along on how Snowflake is improving price for performance by checking out the SPI page. Thanks for watching.